Hello all. I may be using Noiter as a bit of a crutch, but let's go through and speak about a comment. The comment is, at about 12:30, you say game developers know how to do frame buffers, but get suspicious about not having to do something else. At this point, could you talk about split compute? You mentioned the friction points. Please tell us more about those. Tell us stories from when you were going through at Sony. Got to be careful with those. A lot of NDAs stuff there. When you get into talking about developers having to do different things with renderers, this is actually my biggest secret hope for Decade. I see the modding community, VR, pancake worlds, really hoping Decade uses the hardware, 3D geometry into VR geometry. Can you tell me if this is possible? Universal render mod, motion controllers. Of course, there's where you give us a wink wink. You have some unfortunate edits around why the link is poop. Quest messaging with what? Steam link statement. Okay, cool. As I said, the comment there is on the screen, so you can get all the bits. The big question is, for what you are building, are you planning using split rendering? The answer is no. So split rendering is a technology I think will come to the fore in its own form, but it kind of already has. So split rendering, there are various different versions of it. I am not the most educated on the topic, and I don't feel like I'm the best to outline it. Unfortunately, when I was looking for good, easy to digest stuff I could share with peeps, there was some papers, but like it gets really complicated, and I'm really worried I'm going to misrepresent the paper. Short version is, Apple is kind of already doing it, but not actually. So what I mean by like developers know how to do frame buffers is ultimately a graphics engine at the end of the day produces a 2D image. For VR, it's a special kind of 2D image, and you can actually, with Vulkan multi-view stuff, or the various graphics APIs have multi-view things, so provide multiple frame buffers, and then it does the sort of compression and recombination stuff there, and then yeah, those are sent over either the sort of the DisplayPort HDMI connection, or they're sent over through a streaming API like a Link API to the headset. Now, Apple, and I think, honestly, I hate this, but it's a good decision, because most programmers are shit. Most programmers cannot hit VR frame rates. It's a hard thing to do, right? It's a specialist field, and Apple knew that the quality of their hardware would be affected, or the perception of the quality of their hardware would be affected by bad code, right? And they knew, because they were hoping to attract these people, they knew they were going to bring in a lot of like iPhone devs to the VR world, and a lot of these people don't have a lot of high-end graphics experience. So the default in Apple land is you basically provided a scene graph. So you provided a scene graph with a bunch of 3D models and stuff, and then the Apple renderer does everything. This has a lot of benefits. It gives Apple a lot of control. It allows Apple to very easily merge and mutate scene graphs for various sort of complex UX stuff to like make the spatial reality stuff, the mixed reality stuff, work cleanly. And it means that if you have multiple scene graphs from multiple apps, you could, in theory, like splice and merge them in interesting ways. There is a lot more you can do with a scene graph than you could potentially do with a frame buffer. And in a world where you had a cloud rendering situation, whatever, you can, like most 3D applications, the scene graph doesn't actually change that much. If you were to think about the scene graph in first principles, most situations, the data throughput of the scene graph is very small, in the sense of like, if you have a scene with a bunch of monsters and you've got a gun and you're running around trying to shoot them. Really, it's like my character's motion, like position on the screen here, where I'm pointing, and then like shooty shoot, and then there's a bit of things of like, oh, that particle effect is running or whatever. Like, you can compress data down in a scene graph really, really easy. Now, that's quite a simple way. Apple provides access only when you're in fully, they've got this concept of like a 2D window in 3D space, a bounded 3D volume, and then an unbounded volume. And only when you're in unbounded volume, what the rest of the world would call VR, are you able to really just provide them a frame buffer and say, don't worry, I know how to render things, let me render things. What this means is that everything that is being rendered by the Apple system will hit frame rate, because they'll just not render some things, or they'll, they have a lot more control of the frame rate in the experience. But it also means the look and feel of things is a lot more restricted. Now, there's a lot you can do here with custom shaders and such, but like a lot of rendering techniques really come down to like, what is your lighting situation? Are you doing any post-processing effects? There's a lot of ways that we add character to. There's a lot of ways we add character to a visual image. So that's the. I want to say the easy way of doing split rendering is to send through a scene graph, and it's a totally viable way. It's not invalid. It's a version of the future we could see. So, for example, if you were to talk about something like VR chat, which is based on Unity, or if you were to talk to something like Resonite, which is similar, or Meta's Horizon or whatever, there is a world where that kind of platform could work based on a scene graph rather than having a common engine framework and then like scripting libraries. There's some pretty good like papers and theoretical stuff of like what should the application layer be providing in these kind of multi-user environments where we want content to last for a very long time. We don't want to have to it's a flummoxing potion, screw that. We don't want to have to constantly like patch and update all the content. We want content that's more long-lived. Do we move to a world that's more like the web and HTML, where instead of websites sort of providing images and stuff, you're providing what was called the document object model format, the tree, that, the DOM as it is described. That describes the document, very sort of XML thinking, like in a scene graph or whatever, or are we going with something a bit more, implementation specific, so to speak. And game developers really don't want to give you a scene graph. Game engines aren't really built to work that way. It feels funny, it feels restrictive. So there's always going to be pushback from game developers. It also is very locked into your specific platform. So if Apple or Sony or Steam or anyone does this, the reality is, unless there's a common standard, and the first version of a thing is never a common standard, you're probably locked into whatever walled garden they have. And given the state of the internet, the state of the tech investment community, there's very little incentive for them to develop an open standard, right? There has to be a pretty strong commercial incentive for that to happen. So what does split rendering look like in some other format? Like, where could it come from, some other thing? So the other thinking is if you're working with, say, AMD like Sony does mostly, or you're working with NVIDIA, so graphics cards already have a fairly sort of firm API that we speak to them with, whether it's Vulkan or whether it's OpenGL, whatever. I'll use the Vulkan terminology because I think it's the more modern here. we basically say to the graphics card, hey, here, I'm going to send you a texture, and sending textures or model file data is really expensive, and we don't do it every frame. We do it as little as we can. Sometimes there's a texture we update every frame or whatever, but we minimize it as much as we can. Now, even though we minimize it as much as we can, for most traditional, say, PC games, the reality is that our throughput to the graphics card in terms of memory I/O that goes back and forth tends to be significantly higher than a single frame buffer. So even if we were to somehow split off, like let's say like the how do I say this nicely? Let's say we would take the Vulkan API and we were to like work that into the streaming, like the split rendering sort of infrastructure. How do we ensure that so by default, if we were to use it as dumbly as like the programmer is unaware that this is happening, we are by default just, taking their interface to the graphics card, and now NVIDIA or AMD is sort of splitting the work between the local GPU in your PC, say, and a small GPU in the headset, right? A mobile GPU in the headset. Totally doable. It's something that has already been researched by people. But the problem is that by default, the amount of memory that is going over that API, the amount of data that needs to be streamed, is higher than encoding the frame buffer. So that's a problem. It's not, however, it doesn't always have to be that way. So there is a world where, let's say, that you're rendering with Vulkan, you're still using your own custom engine, your own custom graphics API, but you know that if you're sending a texture or something over the thing, that you've got a limited amount of I/O bandwidth that can change sort of frame to frame. And if you go back and you look at like Game Boy and like some older consoles and whatnot, the reality is like very little changed frame to frame. And this is made easier when the device that you're talking to doesn't just use its video RAM to store the textures and stuff. Let's say that it's actually using a bunch of other slower, cheaper RAM to store long-term stuff, and you effectively have like a local texture model cache thing. And so you can say let's say we were to implement it with like a Quest, right? With the support of Qualcomm and everything. You could basically say, hey, when I'm booting up the game, over the course of the startup screen and going through the menus or whatever, I need to provide, I don't know, say a gig or so of assets to the remote device. But then as the renderer goes through and has to render everything, you're sending effectively like your command buffer, you're sending like your graphics programming commands to the headset, and you're not having to send all your texture memory and things on. And hopefully any manipulation of stuff you're doing, because quite often we like manipulate texture memory for things like shadows and things like that, you're doing with modern compute where the GPU is writing locally on the device, on device memory, like what is changing, right? So you could, for example, write a compute shader that is, like if we were playing Noita, say, and there's a bunch of destructible terrain, and you're trying to do like calculations of like how that fire burns and how things get deformed and changed over time, and particle systems, and there's a bunch of memory. You're doing that all with compute memory, and the results are stored locally, and you don't ever really access them. Maybe there is a fetch API that uses the same sort of bandwidth and link to go over, but again, you want to keep it small, because this whole system, by principle, only really works if the amount of data, and it's only really worth all this extra effort, if the amount of data you're sending at a high speed back and forth to the device is less than a frame buffer. All right? Now, as resolutions of headsets go up, the target number of the frame buffer goes up, and the other advantage is that you could probably tolerate in a split rendering situation a slightly more spiky back and forth input, in the sense of, if a frame or two, you have some textures going that are a bit slow to load, or you get a problem, you prioritize the traffic that is like, here's what we need to render this frame, and then what you do is you're like, oh, but we're missing this texture is only partially uploaded. Okay, we'll use like a mipmap of that texture, because there's a bunch of like GPU formats where you have mipmaps encoded, and we prioritize sending the smallest mipmap, so we always have something to render. Or we use a placeholder texture, and you get like shader popping techniques and things like that. Like, there's a bunch of ways when you're in this sort of smarter split rendering world to sort of mitigate those little bits of performance spike and such. But ultimately, the whole system only works if the amount of data transmission happening between the headset and the computer is less. And then the thing we haven't even covered is, how do you bring the power of the PC into this equation? And now part of the thing is like, well, okay, you can say all the CPU work is being done on the PC, and the renderer is now effectively just doing some GPU work. GPU work is actually quite a lot of work, though. So you're like, okay, well, now maybe in the split rendering world there is some pre-calculation I can do before sort of sending stuff across. And this is where we start to get into stuff that's probably a bit too detailed for this video, and it's hard to talk about without talking about NDAs and stuff, but there is some research out there. Basically, anytime you pre-compute things, typically the memory of the computation is more than the sort of equation to make the memory happen. And so then we're back into the problem of, oh, but now, is it worth a split renderer, or do we just send the frame buffer and da-da-da-da-da? And we're in that whole back and forth land. Now, this might all sound like I'm really negative on split renderers. I'm not. I do actually think they will be the future. But it requires a lot of sort of thought and compromise and careful design, and you can see why it hasn't just happened, even though we've been speaking about it for a long time. It's a very complicated topic. And how you slice that, how you slice the problem, all of the sort of, because there's a lot of lines I've talked about, like where do you draw the line, is an intensely opinionated technical discussion, and everyone I've spoke to in the field draws the lines in different places. Sorry, I had to pause there because my brain was getting really intense. Okay, so very simply put, what do I personally think line drawing wise as a thought experiment exercise it would look like? Let's talk through the Vulkan API. So I think your vertex shaders would all still run primarily locally, right? Because the transformation of what vertexes doesn't increase the amount of data you're sending. Now, this does mean that you're still sending a lot of vertices across every frame, and I think there is a world where maybe some vertex shaders could potentially run, but I think they're more likely to be like geometry shaders that run remote. But I think traditional vertex shaders, I think there's enough bandwidth, especially with relative compression and everything, that the vertex shaders still run locally. Then I think there is an API where, much like in the Vulkan API at the moment, we have this concept of host and device memory, where it's like, this is memory that's on the CPU, this is memory on the GPU, right? And obviously this gets a bit more complicated when we start to talk about like PlayStation 5 or system-on-chip systems where we have unified memory, but let's skip that for now. There would be a third memory pool added conceptually, which is remote memory, right? And anything that is referencing purely, anything that's referencing device memory basically has to run locally, and then the stuff referencing remote memory can run remote. It would require that developers think more about their memory budgets. I do think the texture MIP transfer stuff would come into it somewhat. And then, brains, finally. Yeah, vertex shaders, they'll go through yeah, and I do think there will be some per frame data transmission of texture buffers. Now, the per frame data transmission of texture buffer stuff, I think will be limited significantly because of bandwidth issues. As I said, it only makes sense if you're sending less than the frame buffer in reality. But there is a lot of techniques of expressing shadow and lighting calculations, which is what a lot of your frame time is spent up doing, especially if you're doing anything with dynamic, like environment lighting and stuff. I think there's a lot of ways to compress the results of those of that work and send it along. I think the only people who could implement a split rendering architecture is basically a platform holder that has significant pull to make developers work in a certain way. I think the first devices that support split rendering, if it's not a games console from someone like Sony, will support both split rendering and not split rendering, just because the realities of wanting to be backwards compatible with the market, so to speak. And it would require intensive work from whoever the graphics chip provider is, and I think it initially has to be done in console land or in dedicated hardware land, and then it'll come to PC later through sort of standardization, much like a lot of other things like direct memory access and stuff have. And I think it's useful go beyond VR. I think it'll be used for a lot of mobile and cloud rendering applications. And I think a lot of stuff will embrace it quite heavily because there is a strong appetite for commercial reasons for cloud rendering to work, even though people generally haven't been like super fond of it. Like there's a lot of players who economically want cloud rendering to work, so there's a lot of providers desperately they're looking for like that value add, and I think split rendering is like part of that equation that allows it. So I think VR is a strong case for it. VR makes a good usage for it, and VR I think will be the first use of the tech. But I think the tech will appear in other places. But yeah, that's kind of my rundown of split rendering. I hope I've given everything there. I've tried to not have any awkward brain pauses for like NDA pause stuff, because I've just tried to keep my brain fully away from NDA stuff while I talk about this subject. But yeah, I think I outlined everything there. As always, comment, ask questions and such, because it's it's really useful. Like, I would not have probably gone as in depth into this topic and gone back on it if I hadn't had that copy to read. So again, thanks, Stephen. That's really useful. The Noiter is kind of secondary here, so I'm just going to stop the video here. And yeah, the Noiter is really just a background while I natter on about these topics. So I hope that's useful. Toodles.